Hi, my name is Parker Bogus. I'm an undergraduate researcher in the Tissue Engineering and Regenerative Medicine Laboratory at Northern Arizona University in Flagstaff, Arizona, in the United States. My undergraduate research focused on evaluating albumin platelet-rich fibrin as a therapeutic treatment for osteoarthritis and an in vitro study on human chondrocyte cells. So let's start by discussing the pathophysiology of osteoarthritis, inflammation, and cartilage degradation. So over time, our joints, depicted here as a knee, can experience mechanical stress in the bone, which in the synovium can cause the release of various inflammatory cytokines. Two notable examples of inflammatory cytokines typically released in this cascade is interleukin 1 beta and tumor necrosis factor alpha, which can be seen here. These inflammatory cytokines in the synovium bind to specialized cells that are found in the synovium, two prime examples being a synovial macrophage and a fibroblast-like synoviocytes. So when these cytokines bind to these specialized cells in the synovium, it's going to turn them into a catabolic phenotype, catabolic meaning that they're in a breakdown state. And in the cartilage, this is going to cause a further release of inflammatory cytokines, which lead to joint inflammation and over time cartilage degradation. Now, our cartilage is composed of a specialized cell called a chondrocyte, and a chondrocyte secretes what is known as matrix metalloproteinases. And these matrix metalloproteinases cleave aggregans in the cartilage, which also contribute to cartilage degradation over time. So osteoarthritis is a degenerative joint disease where the deterioration of cartilage is present. So you could think of your cartilage as being a cushion between two bones. So if you're thinking about the knee, when the cartilage degrades, you have bone-on-bone interaction, which can actually be extremely painful and significantly decrease the quality of life for those affected. In recent years, the fields of orthopedics and sports medicine have come up with a treatment called platelet concentrates. And a very notable example of a platelet concentrate is called platelet-rich plasma, or PRP for short. And these platelet concentrates have an extremely high amount of growth factors compared to what is typically found circulating in our bodies under normal conditions. So a platelet-rich plasma injection is created via a autologous blood draw from a patient. So a patient undergoes a blood draw. The blood is then spun at a high speed, typically twice, and it also uses a compound known as an anticoagulant. Now, the formulation of this is re-injected back into the patient, and it's extremely safe because, again, it's an autologous blood draw, meaning that the blood is from the patient, and when it's put back into the patient's body recognizes it as itself. So there's an extremely low risk of immune system reaction, which makes it very safe. And currently, platelet-rich plasma is a gold standard not only for the treatment of osteoarthritis and to slow the progression. Nothing can necessarily regrow cartilage at the moment, but PRP has been shown in literature to definitely slow the progression of osteoarthritis and be able to manage the symptoms that are associated. And also for other sports-related injuries, platelet-rich plasma has been shown to accelerate the healing of these musculoskeletal conditions such as Achilles tears. The one limitation of platelet-rich plasma is its usage of anticoagulants. So an anticoagulant, if you're unfamiliar, is a compound that prevents your blood from clotting. So in an everyday situation, if you're walking down the street and you accidentally trip and fall and you cut your hand, you want your blood to clot because you want to stop bleeding. And then, so blood clotting is actually a normal part of physiological wound healing. So by preventing the blood from clotting, the literature has hypothesized that, okay, even though despite the success of PRP in the clinic, it's actually not maximizing its full therapeutic potential. So this led to the development of a second generation of platelet concentrate. This is known as platelet-rich fibrin, PRF for short. And PRF was essentially developed to eliminate the need for anticoagulants. And currently, it's been shown in the literature that PRF initially indeed has a actually higher release of some very important growth factors compared to its predecessor, PRP. Now, the one drawback of PRF is that despite its initial high release of important growth factors and healing molecules, it degrades quite quickly in the human body. So to address this limitation, a novel formulation known as albumin platelet-rich fibrin, Alb-PRF for short, combines this platelet-rich fibrin layer, again containing all these growth factors and healing molecules, with denatured albumin gel. And it's been shown in the literature that by combining these two compounds, that the PRF actually has Alb-PRF has a sustained release of very important growth factors over an extended period of time. So Alb-PRF to date is the latest technology in platelet concentrate, as it addresses the limitations of its predecessor PRF and PRF's predecessor PRP. So my current study aims to provide in vitro proof of concept that this treatment, Alb-PRF, provides a sustained release of transforming growth factor beta 1, TGF beta 1, that's a very important growth factor, and that Alb-PRF also supports human chondrocyte cell proliferation and migration. So you most likely have heard of platelet-rich plasma. So when did it become popularized, and when did these orthobiologics, these platelet concentrates, become extremely popular and become a household name that's used regularly? Well, in the mid 2010s, the late Kobe Bryant sustained an Achilles injury. I believe it was an Achilles tear, and he, at the time, PRP was of course very specialized. It was only for top of the top professional athletes, and your average Joe couldn't walk into an orthopedic clinic and get it. But Kobe traveled to Germany and actually received the platelet-rich plasma treatment, which accelerated his return to play, and he had extremely successful results following the platelet-rich plasma injection treatment. So fast forwarding to present day, and within the past few years, there have been multiple in vitro studies investigating albumin platelet-rich fibrin as a treatment in vitro. So there's 3 very key studies that investigated in vitro with 3 various cell types. So the creation of albumin platelet-rich fibrin was found in a paper in 2020, where this group looked at Alb-PRF and how it affected human gingival fibroblasts. So human gingival fibroblasts are the cells that make up the tissues in our gums. So it was in a dental application in which it had very promising results. The next very promising in vitro study investigating albumin platelet-rich fibrin looked at it in osteoblasts. And if you're unfamiliar, osteoblasts are the bones that cause bone formation and matrix synthesis of our bones. So these are the bones that actually can counteract osteoporosis, which is the loss of bone. And again, they found very promising results using this Alb-PRF treatment in osteoblasts in vitro. The most recent and most pertinent to this study was a study that looked at this albumin platelet-rich fibrin treatment and how it affected chondrocytes, but it was rabbit chondrocytes. They did it in a in vivo animal model, and it had also very good results. I think the most interesting one of the 4 studies that I've pulled here, also, this was actually fully in vivo. So this study was half in vitro, half on the benchtop, half in a rabbit cartilage model. And this study put albumin platelet-rich fibrin into a mouse, and the albumin platelet-rich fibrin was resorbed, or stayed within the mouse's skin for over 3 weeks. So it had an extremely long resorption rate. So project background, I used human chondrocyte cells because they are the primary cells responsible for maintaining and repairing cartilage in humans. And it's the tissue that is most affected in conditions such as osteoarthritis. So it's a very good model to see if this treatment is a potential therapeutic for osteoarthritis. I did 4 types of assays. First assay, I did an ELISA assay. And an ELISA assay, I conducted to quantify the release of transforming growth factor beta 1 to influence human chondrocyte activity, and provide a mechanism of action to support findings from the subsequent assays I performed. I also did 2 proliferation assays, one measuring metabolic activity, one measuring DNA content, and it was important to do these 2 assays to determine
the optimal concentration of albumin platelet-rich fibrin and human chondrocyte cells in vitro on the benchtop. And the last assay I did was a migration and or scratch assay. And I used the optimal concentration that I determined from the proliferation assays and the migration assay to see if the albumin platelet-rich fibrin treatment promoted the migration of chondrocytes into areas of cartilage damage. And the image on the right here is human chondrocyte cells being viewed under an inverted microscope at a 5 times objective magnification, 50 times total magnification. And this is what fully confluent chondrocytes look like. So how did I create the albumin platelet-rich fibrin treatment? Again, I did not come up with this. I followed a protocol from this 2020 paper, which I've cited here, and then also at the end of this presentation. But after following informed patient consent, I conducted a 20 cc blood draw from a patient. I then spun this blood at 700 Gs for 8 minutes once, and of course, without the use of anticoagulants. And when you spin blood under high centrifugation speeds, the blood is actually pulled into 3 distinct layers. As you can see here, the top platelet poor plasma layer has a yellowish appearance, a little bit more difficult to see, but it's there is called the platelet-rich fibrin. It's also referred to as the buffy coat layer, and this is the layer that contains all the growth factor and healing molecules. And then the bottom dark red maroon layer, this is the red blood cell layer. So the first thing I did is with one syringe, I collected the top platelet poor plasma, so this top yellow layer. I heated this syringe containing this layer for 10 minutes at 75 degrees Celsius, and then I subsequently let it cool for an additional 10 minutes. And by doing this process, I actually created this albumin gel. Now, with a separate syringe, I went and I collected the buffy coat, so the platelet-rich fibrin layer, and I combined the syringe containing the platelet-rich fibrin layer with the albumin gel via a Lurlaw connector, mixed them thoroughly back and forth, which created this injectable albumin platelet-rich fibrin treatment seen here and depicted by number 8. So I think it's very important to understand the mechanism of action of the growth factor that I measured in this study. So again, the growth factor I measured was transforming growth factor beta 1, TGF beta 1. So in the body, TGF beta 1 binds to a tetrameric receptor complex on the cell in the cell membrane, and tetrameric just means that there's 4 receptors. So this growth factor binds to this tetrameric receptor complex. This receptor complex dimerizes, meaning it comes together. When it dimerizes, it autophosphorylates one another. This receptor complex then phosphorylates what's called as SMAD2 or SMAD3. Further, another R SMAD, which is SMAD4, is recruited, forming this trimeric SMAD complex. This trimeric SMAD complex translocates into the nucleus via a nuclear pore and can affect the transcription of target genes and ultimately induce cell proliferation. So, in the context of orthopedic applications and for osteoarthritis, it has been demonstrated that typically once cartilage is damaged, you can't necessarily regrow. You can only manage symptoms before undergoing a surgery such as a total knee arthroplasty, which is AKA a knee replacement surgery. So, and if you could stimulate this mechanism via a growth factor found in a platelet concentrate derived from a blood draw from a patient, if you could stimulate it, in theory, it should slow the progression of osteoarthritis and or accelerate the healing of other musculoskeletal conditions such as an Achilles tear sustained from a sports injury. Now, in contexts such as oncology, which is the study of cancer, this mechanism is actually hyperactive, meaning that this mechanism is occurring even with extremely low concentrations of this growth factor, which can be used to explain why cancer cells proliferate so wildly. But again, in orthopedic and sports medicine context with regards to osteoarthritis or any other sports injury, it's very hard to do. But if you can stimulate this, you could potentially manage the symptoms and accelerate healing of musculoskeletal conditions. So the ELISA assay analysis, the figure on the left is the daily release of this important growth factor, TGF beta 1, from the albumin platelet-rich fibrin treatment. And what I take away from this graph is that on day 9, there's a similar amount of TGF beta 1 release from Alb-PRF as there is on day 0. So in the literature, you've got, okay, this PRF is in theory superior to PRP because it has this high release. As a reminder, the downfall is that the growth factor release quickly tapers off and degrades quickly in the human body. So the formulation of Alb-PRF was hypothesized to be able to sustain, not only have a high release, but sustain this high release over multiple weeks and potentially months. And this assay, you can clearly see that because on day 0, okay, you have a pretty high release, but you look over at day 9 and you're like, oh my goodness, this is actually a very similar release to that of day 0. So it validates the findings and the hypothesis that indeed this, by combining PRF with this albumin gel, it does allow for the sustained release of important growth factors. So the figure on the right is the cumulative release of TGF beta 1 from Alb-PRF treatment. And what's notable here, so how I got this figure, I added each of the releases found on their respective days, added them up cumulatively. So on day 9, there was a cumulative release of almost 90,000 picograms per milliliter of TGF beta 1 from albumin platelet-rich fibrin. And why that is notable is because that's actually one of the highest values ever recorded compared to both PRP and other iterations of PRF. It is notable to say that I measured the transforming growth factor beta 1 from the albumin platelet-rich fibrin gel itself. So I performed a 1 to 10 dilution while conducting this ELISA assay. But as far as how I measured the TGF beta 1, I did not measure it from cell culture medium. I measured it straight from the gel, which can also explain why such high values were found. So the next 2 assays I did were proliferation assays. So the first assay, figure on the left, is a Presto Blue assay, which measures metabolic activity of cells. So I was measuring the different concentrations of albumin platelet-rich fibrin treatment and seeing which one is the most viable for human chondrocytes. For this study, again, I conducted this in vitro, so in a laboratory setting. And to grow cells in a laboratory setting, if you're unfamiliar, you have to use a growth medium. So in my case, I used what's called DMEM complete. So it's a DMEM growth medium combined with 10% fetal bovine serum, FBS for short. And that is what composes the control. These different conditioned medias, or just the dilutions of that albumin gel, that yellow gel-like substance, with the growth media, DMEM complete. And that's how I obtain these various treatments. And what I found from the Presto Blue assay was that the 20% concentration had significantly more metabolic activity compared to that of the other treatment groups, and then, of course, also to that of the control. Although not statistically significant like the Presto Blue assay, the Cyclone assay, which measures DNA content, followed a similar trend. You can visually see here that the 20% treatment had the most DNA content compared to that of the other treatments and to that of the control. So following this, I did a migration assay comparing the 20% albumin platelet-rich fibrin conditioned media to the control medium, doing a migration assay, also known as a scratch assay. So this is a depiction of a migration assay. So what you do for a migration assay is again, we're growing cells in vitro on the benchtop. So you grow cells to full confluence, depicted in the pre-scratch image. Then you take a pipette tip, a P200 pipette tip, and you scratch this monolayer from the 12 o'clock position to the 6 o'clock position, which stimulates a mock wound. And then I let the cells remigrate with their respective treatment over 40 hours. And I captured images at hour 0, hour 20, and hour 40. So these are the migration assay images for the control. So again, this is just normal DMEM complete. These chondrocytes are in that growth medium. So figure on the far left is time point 0, hour 0. So you can clearly see the wound bed induced by the P200 pipette tip. Middle image is hour 20. So you can start to see the migration of the chondrocytes into the wound bed. And then far right is hour 40. So you see that the cells have migrated approximately 70%. So the wound is approximately 65, 70% closed. Now, the next slide shows the migration assay images for the 20% albumin platelet-rich fibrin. And again, this was determined through the the two proliferation assays I conducted. So again, far left figure here is hour 0. It's a little bit harder to see. You can see these platelet-rich fibrin chunks, and that's these yellow molecules that are floating around. So you can still see there's a huge open space. Hour 0, hour 20, the middle image, you start to see the migration of these chondrocytes into the wound area. And then notably, hour 40, the wound actually completely healed. So there's 100% wound closure. So this migration assay is very pertinent to osteoarthritis because, as a reminder, osteoarthritis is cartilage degradation. So by inducing cartilage degradation, because again, cartilage is made up of chondrocytes, so by inducing this trauma and this mock wound and resupplying with various treatments, I'm trying to determine that, okay, does this normal growth medium or does this um, treatment group, does it allow for the migration of these chondrocytes into this wounded area? So it's mimicking osteoarthritis in vitro on the benchtop. And we could see this qualitatively in these two slides. So quantitatively, figure on the left here is measuring percent closure up to 100%, of course. So this is the figure on the left is at 20 hours. So the 20% treatment group, although not statistically significant to that of the control, did close more compared to that of the control at 40 hours. However, again, still measuring percent closure of the cells. The 20% treatment was statistically significant to that of the control, meaning that the treatment significantly enhanced the ability of these chondrocytes to go into this wounded area and to heal. So results and discussion. So the albumin and platelet-rich fibrin treatment promoted the steady release of TGF beta 1, which is that very important growth factor. And it also increased human chondrocyte proliferation and migration. So unlike PRP and earlier iterations of PRF, which typically lose bioactivity within 24 to 48 hours, meaning that initial growth factor release drops off, albumin platelet-rich fibrin maintained this release of this very important growth factor over 9 days, suggesting it as a superior platelet concentrate, at least in vitro. Albumin platelet-rich fibrins enhanced stability and bioactivity, suggest it to be a strong clinical potential treatment for osteoarthritis. Future studies should explore in vivo efficacy and compare Alb-PRF to PRP in cartilage repair models. So, of course, these are some fantastic in vitro results, but not everything that has fantastic in vitro results, of course, translates to the clinic and to the bedside. So further animal in vivo models are needed to see, okay, how, or and to evaluate the translation of this treatment to hopefully one day make its way into the clinic. So overall, this in vitro study highlights Alb-PRF's potential as a therapeutic treatment for osteoarthritis in orthopedic and sports medicine applications. So I mentioned the translation because, of course, not only with platelet concentrates, but also in other areas of cellular and molecular medicine, not everything that has fantastic results in vitro on the benchtop translates to the bedside and to the clinic to improve the quality of life for patients. So this is the current clinical translation of platelet-rich fibrin. Again, earlier iterations, not albumin platelet-rich fibrin, but earlier iterations of platelet-rich fibrin in orthopedics. These are two clinical trials that came out in 2023 and 2022, so quite recent. So first study I pulled was this study showed that compared to arthroscopic rotator cuff repair alone, the application of PRP in arthroscopic rotator cuff repair reduces re-tear rate and improves clinical function scores, whereas the application of platelet-rich fibrin PRF has no clinically meaningful benefit. Another study also found, moreover, platelet-rich plasma could be recommended in meniscus repair augmentation compared to platelet-rich fibrin matrix. Platelet-rich fibrin matrix was shown to have no benefit in improving functional outcomes. So, in theory, the platelet-rich fibrin in vitro showed, okay, there's a much higher release of growth factors. And so, in theory, it should be superior to PRP, at least earlier iterations. But obviously, we're seeing from clinical trials that this isn't not always the case. And currently today, platelet-rich plasma is still the gold standard, not only for orthobiologics for the treatment of osteoarthritis, the management of that, but also for the acceleration of healing for other musculoskeletal conditions. So it's important to keep that in mind as far as the translation. A few acknowledgments I'd like to make. I'd like to thank my research partner, Maddie Watt for her help on this project. I'd also like to thank my two mentors, Dr. Aaron Tabor and Dr. Robert Keller, for their mentorship throughout this project. And I would also like to thank the other members of the NAU Term Lab. For funding sources, the NIH funded this. There was a grant to Dr. Robert Keller, NAU Gene Schroller Research Mini Grant to myself. I'd like to thank Development Engineering Sciences for providing additional funding to carry out this project. And I'd also like to thank Dr. Aaron Tabor and Axolotl Biologics for generously donating human chondrocyte cells for the usage in this project. These are my 27 references. Thank you for listening. I hope you enjoyed and have a great day.